Hello, and welcome to today's webinar, Signal Simulation and Testing, Fundamentals and New Frontiers. This is brought to you by our sponsor, Spectracom. I'm Bethany Chambers from GPS World parent company North Coast Media, and I'll be your event manager today. Before we begin, I'd like to go over a few ways that you can participate during today's presentation. Although you are currently in a listen-only mode, we encourage you to ask questions throughout the presentation. Just type in the text box at the bottom left, then click Submit to place your question in queue. You can also submit questions via Twitter using the hashtag GPSWorldWebinar. Questions that were submitted during registration have already gone to our panelists and may be covered in this webinar. Some questions may also be answered in an upcoming issue of GPS World magazine or in one of our e-newsletters. We strive to answer as many of your questions as possible. If you experience any technical difficulties during today's event, use the same Q&A box at the bottom left to tell us about your issue, and click Submit, and assistant producer Joelle Harmsry will personally assist you. Finally, a recording of this webinar will be available tomorrow afternoon at gpsworld.com/webinars. You can get to that page now and bookmark it by clicking on the GPS World logo in the top left of your screen. A link to the on-demand recording will also be emailed to you when it is available. Now I'd like to turn today's event over to our moderator, GPS World Editor-in-Chief, Alan Cameron.
Thank you, Bethany, and welcome everyone around the world. I see we do have truly global attendance from the Far East to the Mideast, spanning North America and Europe. We've got listeners from around the world today. Welcome everyone. And thanks to our sponsor, Spectracom. Today's webinar is Signal Simulation and Testing, Fundamentals and New Frontiers. We'll be hearing about both subsets of simulation and testing, the fundamentals and the new frontiers. We're going to open up today with John Fischer from Spectracom, who is going to talk about specifically about spoofing and simulation of spoofing. Spoofing is an increasing worry. We could see that reflected in conference papers and company R&D around the world. What is the future? We don't know how much spoofing we're going to encounter, but it's certainly a potential. And when you don't know the future, it's important to trial a few things to figure out what, so that you're prepared for the future. And spoofing is one of the challenges that John Fischer from Spectracom will address. We'll hear next from John Pottle from Spirent on behalf of Spirent Federal. He's going to talk about the fundamentals of good testing, how to set up things to think about as you go about setting up your testing campaign. We're going to round out the presentations with a case study from Racelogic. Julian Thomas from Racelogic is going to talk about work that his company did with the Swedish Space Corporation involving rockets and simulation there. Then we'll have the final quarter of the hour will be your questions and their answers, and we look forward to an excellent participation from everyone. I'll turn the floor over now to John Fischer from Spectracom. John, tell us about spoofing.
Thank you, Alan. I'm going to talk about testing for spoofing, but before I do, let me just give you a quick background on Spectracom and who we are. In a single sentence, our mission is to simplify the integration of position, navigation, and timing into our customers' systems. We don't make GPS receivers, but we make a lot of the things that surround them. And in fact, one of those peripheral items is a GPS simulator, which I'm going to tell you about. And so our goal is always to support our customers to enhance the resiliency of mission-critical PNT things. So combating spoofing is an important part of that. So let's get into it. What is GPS spoofing? And I'll say GPS. I should also really be saying GNSS is really, because GPS is just one of the several now global navigation satellite systems. So please excuse me where I still sometimes use the shortcut of GPS when I really should be saying everything applies for GNSS. So spoofing is when you attempt to deceive a receiver by broadcasting fake navigation signals, and you're going to try to do probably something bad with that. So for testing, the two applications that you're usually using test equipment for one is to harden your receiver. If you're a receiver maker or even an integrator of receivers, and you want to make sure that you have some resistance, you're not vulnerable to spoofing, you want to test for that. And so that's one area. Another area is in defensive operations, that you can actually use spoofing to take control of an unmanned airborne system and deflect it or redirect its path. Now, I'm not going to, in this presentation, I'm not going to focus on that aspect of focusing on hardening, but it's important to note that a simulator is a spoofer. You know, the same equipment that you're going to be testing with when you use a simulator can be used as a weapon. So we always like to point out it's very important, we have to all be very careful about keeping simulators and jamming equipment out of the hands of bad guys. But having said that, I do like to point out that spoofing is very hard. Jamming is easy. So we all know these GNSS signals are very weak and they're easy to jam. Spoofing's a lot harder, but it's also more treacherous, more dangerous, because you can, if it goes undetected, you can really be in trouble. So when we're talking about spoofing, there's three critical parameters to deal with. Time sync, about how well your spoofer is synchronized with the live sky signal. Position, how well you're tracking the position of the vehicle that you're trying to spoof. And the power level, how well are you matching the power level to the live sky. Now, in the example I'm using a UAV thing, because that's kind of the high-value target today, but all of this holds true for whatever you're trying to spoof. So the whole issue here is about capturing the receiver. You're either trying to capture the receiver in its signal decoding or somewhere in its navigation solution. So what the spoofer has to do is it has to enter into that capture range of the receiver, first get the receiver to lock on the fake signal, and then pull it off. So let's focus now. Let's start with each one of these. For time sync, this is the idea that, okay, the live sky is transmitting from each satellite synchronized signals that it's giving you're measuring the way you measure your position on Earth is you're measuring the time delays from all the satellites and determining your position from there. So any receiver that's tracking that, you now have to enter into that tracking capture range and be synchronized and have your simulated satellites being locked into there as well. So how well a receiver will track that, or let me put it a different way. A receiver that doesn't discriminate on this time sync delay is very susceptible to spoofing. A receiver that requires the spoofer to be very accurately time synced to the live sky is very resistant to spoofing. So that's one of the critical parameters you want to measure when you're seeing your vulnerability of your receiver, how well that goes. The next one, similar idea, is the position. And your simulator is going to create fake satellite signals that make the vehicle think it's at a new position. How much error it can be? It first has to start at the vehicle's current position and then pull it off. Well, how accurate does it have to be in establishing that initial position? If for example, a receiver that requires 500 meters of accuracy in that fake signal before it will be fooled is better than one that has 800 meters. So another important test to do, run this thing to see how accurate the receiver would be. And a lot of times when you're running this test, you have to look at how long has the system been tracked. And there's also factors of velocity, acceleration, and things like that. But in general, you're talking about what is that initial, simplest one to do is initial position error and seeing how well it rejects things. The third one, of course, then is power level. So typically, again, you are going to capture the receiver. Your spoofer is going to want to be start out at probably at a little lower, at the same as a live sky, and then typically it raises its power level, gets stronger, and then it becomes the dominant signal that the receiver is tracking. So there's usually some level, 2, 3, 4 dB that stronger than the live sky that you have to do to measure. But if you go too strong, again, some better receivers might recognize that as spoofing, and so that becomes one of the countermeasures that a good receiver can do. Or if you become so strong, you're actually jamming the receiver and jamming out the live sky. And so, again, a receiver that's jammed then may do other things anyway. So there's usually a very narrow window in the power level, and when you're dealing with a moving vehicle, that has to be dynamic. You have to control that power level dynamically. So let's go to what a test system would look like, and kind of two main ways that you can set up a test system. One is where you have, my method A that I show here is that we have two simulators. One simulates the live sky, one simulates the spoofer, and then you have some synchronization equipment. So I'm gonna go into that one in detail because that's the one that is the best thing for really making accurate measurements of where you have full control over power level, time sync, positioning, velocities, everything. So that's the preferred way of testing. Method B that I show here is where you're really using the live sky. So this is the realistic way. This is the way a bad guy would be doing spoofing, where so it's very realistic. But as I said, spoofing is hard. It gets complicated very quickly. You will have to, if you're doing it with a moving vehicle, you're having to track that vehicle. You have a lot of variables now with power levels changing and positioning changing, and all these parameters are changing at once. So it's much more difficult to do testing in that way. So what does that A configuration look like? Here's this diagram, and it shows that I have two spoofers here, or excuse me, two simulators. One is the spoofer, one is the live sky. We take the RF output of each one of those simulators, combine it, and feed the receiver, so you have that. And then the two simulators need to be synchronized. Again, the synchronization is one of those important parameters. And then we have a PC-based test scenario controlling all of this. So in this way, we can vary the time sync, we can vary the position, we can vary the power levels of the spoofer simulator in comparison to the live sky simulator. So it's actually a full test system, quite affordable, something you can evaluate a receiver's vulnerability, or also evaluate any kind of countermeasures that you might be doing, either within the receiver or maybe within the other larger system that you're integrating your receiver into. So if you're like me, when you're listening to webinars and you get a lot of interruptions and you weren't hearing everything I said before, I'm going to just give you the three big takeaways that you want to hear of what I was talking about. Is one, hardening receivers is very important against spoofing, against jamming. Very important. You need to do that. And using testing with a simulator is a very effective tool for doing this hardening, for designing better features in your receivers, for evaluating different countermeasures things there. And it's important that this is a new threat, and it's very real, and it's increasing. And I have here, I show a quote here from a Department of Homeland Security official recently emphasizing this fact. So, I'll just want to reiterate the importance that keeping spoofing and jamming equipment out of the hands of bad guys, regardless of how much money they have. It's an important thing, and I think it has to start with this community, and we take this seriously at Spectracom. So thank you for your attention, and I will now turn it back over to Alan.
Thanks very much, John, and thanks for that presentation. We'll have questions and answers on spoofing and the other subjects presented in the final quarter hour of this broadcast. Meanwhile, we're going to turn to John Pottle from Spirent Communications, speaking about the fundamentals of good testing. John, take it away, please.
Okay, Alan, thank you very much. Hello, everybody. I'm speaking to you here in the UK, where Spirent is based. And as Alan said, I'm speaking partially on behalf of Spirent Federal, as well as Spirent Communications. So for those of you who don't know Spirent, we're a communications test company and focused on test solutions that really help the world to communicate faster and more reliably. And that applies to navigation and positioning, equally to wireless and fixed networks. So what I'm going to talk to you about today is, well, an interesting counter, if you like, to what John has just presented from Spectracom, because he was talking about spoofing test, which is fairly, very interesting and also fairly advanced. I actually want to go right back to basics, fundamentals for good testing, because we find increasingly that as GNSS becomes more popular and more widely used, people ask us more fundamental questions. What tests should I do? How do I get going with my testing? So that's really what I'm going to cover in the next 10 minutes. So to set that up, here are some statements that have been published online. You can find them if you Google something along the lines of GPS receiver specifications. And I set the search window to the last month, so literally in the last month. And here are different manufacturers. I've anonymized them, but different manufacturers of real GPS or GNSS system specifications, how they're presenting their receivers. And, well, just look for a minute at the time to first fix between these examples. The first one talks about a sub 1 second time to first fix. The second one talks about a sub 45 second time to first fix. The third one's a bit non-specific, but don't worry, they're above competitive offerings in many ways. And the fourth one talks about 10 minutes time to first fix. Well, I would submit that's pretty confusing data to people who are trying to ask the question, what receiver might I select and which one's best for my application? And we get asked this question all the time. If there are any receiver manufacturers online, rest assured we don't make recommendations on receivers. We're agnostic in Spirent. We help people decide. So step 0 that we always recommend in rationalizing this landscape, if you like, is to document your requirements and priorities. And I'll come a bit more onto that in a couple of charts' time. But until you've rationalized that and become really clear about what's important for your application or your system, then it's, I would say, impossible to start making a decision about what technology, receiver technology to choose. And you can see from these quotes how vastly different the capabilities are, and for good reason. So one thing that many of you are aware of, I'm sure, is that for standalone GPS testing, there really are no accepted global standards. There clearly are standards for wireless and other wireless communication technologies like Wi-Fi or Bluetooth, for example. And there are clearly standards in, for example, aviation communities and other market verticals. But for the fundamentals of how do you test and present results on a GPS receiver, there really are no standards. At least we're not aware of them, if there are. So what are the most common tests? Well, most people would run these 5 tests in order to characterize their receiver. Time to first fix, acquisition sensitivity, tracking sensitivity, time to reacquisition, and static position accuracy. Some of them are pretty self-explanatory, like time to first fix, although there are different colors to that, such as a cold start, a warm start, or a hot start on a receiver. Acquisition sensitivity, broadly defined, is the lowest power level at which a receiver can acquire a position fix. Tracking sensitivity is the lowest power level that a receiver, having acquired a position fix, can continue to track the satellite and provide a position. And I think the other two are fairly self-explanatory. If anybody wants more information on these with definitions, we do have white papers and other documents available, so just feel free to look online, spirent.com, or send me an email, and I'll be happy to provide further information on the definitions. So I said I'd come back to this question of documenting your test requirements, and let me do that through this chart. And what I want to suggest is that the performance requirements and priorities can be widely different depending on the application segment. For example, a survey receiver would be very interested in very accurate position information down to the millimetric level. But actually in a survey situation, time to first fix would generally not be important. Another example might be an automotive application where for navigation in the car, you may need accuracy of perhaps 5 meters or even a little bit worse, maybe up to 10 meters. On the other hand, if you are trying to use GPS for lane guidance, or even more accurately for a degree of autonomy where safety comes into play, as well as just driver information, then often the accuracy requirements are somewhat higher. So I think you can see from those few examples that I just cited that you get very different user requirements from the system depending on the application based on those fundamental tests that most people would run to characterize their receiver. In terms of which test system or approach to use, well, at the highest level, there are 3 generic test approaches. Live sky testing, testing using a simulator, which that's what you just heard about from John at Spectracom. although he did present some live sky with simulation. And then record and playback. And this table seeks to share with you the high-level pros and cons of different approaches. Live sky can be attractive because it's realistic, and nearly everybody would do live sky testing before releasing a new system or application or device. The benefit is it's very realistic, but you can't control the signals in live sky. You can't, at least not legally, do a spoofing test. You don't have a reference true position information, and it's not repeatable because the satellites move around, giving you different test conditions and particularly geometries and weather conditions, for example, test to test. For what I guess I might call parametric testing, where you actually want to take repeatable measurements, then you really need to look at simulation or record and playback. Simulation has some fantastic advantages. I'm saying that because Spirent is a simulator company, but I'm also saying it because it's evidenced by the fact that so many people rely on simulators for their controlled R&D testing. It's repeatable, you have control, right down to the nav data message type or the signal conditions, and it's also gives you a reference truth position, so you can compare your results with a reference position. The snag with simulation is that it's representative of the real world, but it's not an exact replica. So if you want a particular location exactly reflected in a test setup, then you can set up a representative view of that in a simulator. But to get the real deal, you've either got to go out in the real world, live sky, or you can use record and playback, which is partially controllable. Record and playback systems, which sample live sky and then digitize the signals and replay them in the lab. It's realistic, but it's only partially controllable. And also with record and playback, I believe, looking at some of the questions coming in here, there are going to be questions on multi-GNSS. Well, record and playback can't capture signals that don't exist. So for future signals and future satellite systems, you've really got to resort to simulation as the only approach. Again, if people want more information on the pros and cons of these different approaches, I can forward some offline. So in the few minutes I've got available, I have time just to dip in to a bit more detail. And I've chosen, of the 5 generic fundamental tests, I've chosen just to dip in a little bit to static position accuracy test. And just to put a little bit of color on that, the aim of this test, which is one of the fundamental KPIs, is to test the accuracy of a receiver. So in order to do that, you need a truth position. So you know exactly what the real position is that the test is in, and you can get that from a simulator. You also need to think about whether you do a cold start, warm start, or hot start, or combination on your receiver. And the other thing I wanted to mention with this scattered diagram here is that because of the way GPS receivers work, by searching for signals through an algorithm, you're not going to get the same accuracy or time to first fix, for that matter, etc., every time you run a test. So running multiple tests, even hundreds of tests, and then taking a statistical view, which is what those red and green circles show, is the best way to test. If you just do one test, and you're unlucky enough to get an outlier, you may reach some wrong conclusions. The type of test setup that you would typically use for a time to first fix test, I'd say I would recommend a simulator. And using a simulator, you can generate an RF signal to your device under test, just showing a PND type system here. And the position information would be reported by the device under test. But equally critical, you get from the simulator what we call in Spirent the truth data. So the actual position versus the reported position, which allows you to analyze the spread of position accuracy. So this setup, it says time to first fix. It applies equally to static position accuracy. The receiver data that you'd want to look at would typically be from a NMEA sentence. This example here is a GGA sentence, which is presents essential fix information. And you can see there, box number 2 is latitude, number 4 is longitude, and number 10 is height. That's reported by the receiver. For different tests, you would typically look at different NMEA sentences. And at the risk of sounding like a broken record, we've got a lot more information available on this. So if you're interested in getting into detail, if this topic is of interest, then just let me know, and I'll be happy to share that with you offline. So what I hope I've presented is a flavor of the kind of thinking behind how to do some meaningful testing that's simple to start with and progressive, and that allows you to determine whether you're getting the results and performance that are appropriate for your receiver or system or application. Setting the objectives that are important for you and your priorities, I would suggest, should be step number 1. Planning what test tool or test tools to use are as important as setting up the test scenarios. And then having done that, rerunning the tests multiple times. We normally recommend 100 times or more with some statistical analysis, which can easily be automated either in the Spirent systems or in your own post-processing, is a good place to start. And then we've already heard about spoofing on this call, but there are other vulnerabilities that GNSS systems are affected by. And I don't think we're far off really recommending that some of these other vulnerabilities and testing them is pretty fundamental in the reality of the world we see today, particularly for applications which have some safety critical or commercially important element to them. So with that, I will conclude my presentation and hand back to Alan. Thank you.
Thanks very much, John. We'll turn now to a presentation by Julian Fischer from Racelogic about work that Racelogic and LabSat have done with a client, the Swedish Space Corporation. Julian?
Thank you, Alan. It's actually Julian Thomas, not Julian Fischer. A little slip up there, I'm sure.
I'm sorry, I apologize. Julian.
No problem at all. I'm going to go over an interesting case study where one of our clients has worked closely with us to adapt our equipment to meet their needs. I'm the managing director of Racelogic. We're an electronics company based in the UK, and we specialize in GPS simulation and data logging in the automotive, aerospace, and train industries. To make sure that satellite navigation engines are not used for missiles and guided weapons, there's a voluntary agreement between 41 states to limit the performance of receivers so they stay within certain limits. The limits are a maximum speed of 1,850 kilometers an hour and a maximum height of 18,000 meters. Some companies limit the output of their receivers when either of these limits are reached, and some companies only limit the output when both the speed and the height exceed these values. Note that being a treaty, these agreements are not legally binding. If you have an application where you will exceed these limits, you can pay around £5,000 for an export license to obtain an unrestricted GPS receiver. This license is to check that you are not using the receiver to build a missile to carry weapons. On top of this, you can pay around $5,000 for a suitable receiver. An example of a receiver which can be ordered in an unlimited configuration is the Novotel OEM V1. The Swedish Space Corporation, or SSC, approached us for a system to check that the receiver they had purchased did actually work well above those prescribed limits. Receiver firmware is upgraded fairly regularly to take into account things like leap-second problems and new constellations. SSC found that they needed to check on a regular basis that the limits are still removed after a firmware upgrade, for example. You can see that it would be a disaster if they launched a balloon or even a very expensive rocket and then found that they couldn't track its progress. A little bit more about SSC. SSC are based in Sweden, just outside of Stockholm, and they turn over roughly 110 million euros a year. They have divisions in Sweden, America, Canada, Chile, and Australia. They specialize in managing satellite operations using their own network of ground stations, custom aerospace engineering, scientific services using rockets and balloons, space propulsion, and flight test services for the aerospace industry. SSC use the Esrange launch facility just outside Kiruna in northern Sweden to launch their balloons and their rockets. They're in the middle of a large, sparsely populated landmass, which makes recovery of their products much easier and reduces the chances of landing in the sea. Their Maxus 8 rocket regularly reaches altitudes of 700 kilometers, which is enough to put a low Earth orbit satellite into position, such as an Earth observation satellite. One advantage of the location is that during the summer months, you have 24-hour sunlight, which means that the solar panels on the balloons keep the instruments running continuously. The balloons have a maximum altitude of 45 kilometers and a maximum payload of around 2 tons. They travel with the wind, so at an altitude of 45 kilometers, this can be as much as 200 kilometers an hour. These balloons are used for atmospheric research, astronomy, and weather monitoring. SSC use GPS and GLONASS in a dual configuration to track the progress of their balloons, so they require an unrestricted receiver to continue operation when it goes beyond 18 kilometers in height. GNSS conditions are quite straightforward for the balloon due to the low dynamics involved, so this is the only test they required to validate their systems on a balloon. A more demanding application they have is for the rockets that they launch from the Esrange facility. They can reach altitudes of up to 800 kilometers and are used in microgravity research, education, and instrumented sounding rockets. The biggest rocket they make, the Maxus 8, is almost 16 meters high, over 12 tons in weight, and believe it or not, can carry a payload of up to 785 kilograms, which is quite impressive. The maximum speed they reach is 3,500 meters per second, or 12,600 kilometers an hour. And believe it or not, the rocket motor only burns for 63 seconds in total, producing quite a strong 15 G of acceleration. Once it has reached maximum height, the payload can experience microgravity for up to 14 minutes at a time. Interestingly, when the rocket launches, it is deliberately designed to spin to stabilize its attitude. This creates a very challenging set of conditions for GNSS. Not only does it have to work at the high speeds and altitudes, but it also has to cope with a high acceleration, jerk rates, and yaw rates. The spinning also introduces a phase shift in the satellite signals, which has to be tested on the ground before being used in a launch. This phase shift can skew the measurements and also make tracking of the satellites much more difficult. This is the velocity and height profile of a recent Maxar 7 rocket launch, which they wanted to simulate. And it reached a height of 700 kilometers and a speed of 3,000 meters per second. This is the raw data recorded using a Novotel OEM V1 GPS engine. SSC wanted to test this on their bench before they sent up the next rocket to check that a recent firmware upgrade did not bring back the limits on speed and altitude. We therefore worked closely with them to develop an identical trajectory with artificial satellites using our FatGen signal simulation software. In the process, we had to make quite a few modifications to make it more suitable to the high dynamics and high vertical climb rates required by their test. We started off using their recorded NMEA file to exactly reproduce the trajectory of their recent test using artificial satellites and signals. We then fed this scenario into a LabSat 3, which provided the signals to their Novotel receiver, which then successfully locked onto the RF signal and followed the same trajectory. Then we created a user-generated scenario following the shape of the path of their collected data. This meant that modifications to the trajectory could then be made to simulate other situations. We set the jerk rate to a maximum of 10 G per second, which would then put the Novotel receiver under very high dynamics during the initial 63 seconds burn of the rocket motor. We then sent this user command file to them over email so they could use the FatGen software to modify it to suit their future tests. The other challenge they faced was caused by the constant spinning of the rocket to give stability to its flight. This spinning adds a phase shift to the satellite signals, so they also wanted to test for this on the ground before the launch. As the LabSat 3 is also a battery-powered RF recorder, they are building a rotating model containing the LabSat and a live sky antenna. From this, they will be able to record a real rotating antenna signal and play this back on the bench. This will allow them to repeat the test as many times as they like to see how this affects the performance and measurements of the receiver. The tracking loop of the receiver can then be adjusted whilst observing the output of the receiver to get the best possible results. The LabSat 3 proved to be a versatile tool for testing the challenging aspects of SSC's test environment, utilizing both a live sky recording facility and the FatGen software to create artificial signals, arguably the best of both worlds. SSC only used a single constellation LabSat in their simulations, but the LabSat 3 is also capable of recording, replaying, and simulating GPS, GLONASS, and Beidou signals simultaneously. The fact that the system is small, lightweight, and battery-powered means that some of our customers have even sent the LabSat up in a rocket launch to record real-world signals. We've also supplied LabSat simulators to SpaceX, NASA, and JAXA, the Japanese Aerospace Exploration Agency. All hardware and software is produced in-house, so we are more than happy to take on customer challenges and modify our products to help them test in a more realistic way. Thank you for the time, and I'll hand back to Alan.
All right, thank you, Julian. And that was Julian Thomas from Racelogic and LabSat. We turn now to your questions, and we have ample time, I think, to cover. We've got 3 or 4 main question topics that I see in the flow here. And the first one has to do with, or the first several, I'm grouping several questions together, and I'm going to give our panelists an open invitation to talk about any aspects they wish to of multi-constellation simulation. Here are the questions that we've received. What is the toughest multi-constellation performance parameter to meet? Someone else is interested in special considerations for multi-constellation performance, as we have only performed GPS-only simulations to date. Someone else is particularly interested in solutions that can simulate a GPS L1 and L2 and a GLONASS signal. And the third person phrases the question a slightly different way. What are the main challenges in testing of multi-constellation devices? I'll just throw it open to the panel. Any of you three that wish to address that, go ahead.
Alan, this is John Fischer from Spectracom. I go first. I guess in the multi-constellation, I guess it's probably more of a question for receiver designers. They're the ones that have the real challenges in designing multi-constellation receivers. But we can just share what we've observed of the challenges are having to test for the synchronization between the different constellations. As you may know that each one, GPS, GLONASS, Galileo, Beidou, their time references are just slightly different. They'll report on things, but and they'll report on those differences. It's a very controlled situation, but there are differences, and so making sure that a receiver, it's a challenge for the receiver designers to make sure that they're synchronizing that way. And I guess I would even say there's almost like a couple classes of receivers that are multi-constellation. Some are multi-constellation, but they're only doing one constellation at a time. Other ones are creating a larger navigation solution of where they're using satellites from the different constellations all into one solution. That's the more challenging thing there. And so typically, again, you're concerned about accuracy, and it's typically more of an accuracy dilution problem because you might depending on a lot of factors, you might be making it more accurate by having more constellations, but you're typically, by having more constellations, you're getting more availability. You're seeing more satellites, so your shadowing issues are much less. That's the big advantage of multi-constellation. You can, if you're really clever in doing these like very large matrix solutions, you can combine satellites from different constellations, but that's a pretty big challenge. And I guess the third challenge I would say is more of multi-frequency. As you start doing these more things there, your receivers are now L1, L2, even L5. L5 is even farther away than L2. So, flat normal wideband receiver design issues of flatness and group delay and all those kind of things there that receiver folks are having to design about.
Hello, and thank you for joining us today. We are attempting to troubleshoot some technical difficulties with our live phone line. Please hold with us for just a moment.
I apologize for the difficulty our audience is having in hearing us. We're having some problems on the phone line. We will pick up just again with the presentation just as soon as we are able. All right, I've been informed that we're back to clear transmission, so I'm going to try again, and I apologize to all our audience for the technical difficulty that we had with the audio portion of our program. And I'm going to go back to John Fischer. John, can you please restate what you just said about multi-constellation testing, and because I'm afraid that nobody could make it out. If you'll do that, and then we'll go on to John Pottle and Julian Thomas for their perspectives.
Great, thank you, Alan. Yes, so the challenge in multi-constellation receivers, and again, this is the receiver designers have these challenges, is the fact that each separate GNSS system has a different time base, and they do a lot of things to coordinate and control them so that they match up, or they're at least known differences, but they are different. And so a big challenge for the multi-constellation receiver maker is to deal with those time sync differences and how that might affect accuracy. We've observed that there's kind of two classes of multi-GNSS, multi-constellation receivers. One is where they'll do a one constellation at a time. So that's more of a simple case. So even though they do multiple systems, they'll only do one at any particular time. And then the other class are the ones that are using satellites from all the different constellations and trying to do a more composite navigation solution. It's, again, much more difficult to do, much larger matrices, but can have some real advantages. Now, there is a thing that it might dilute precision by doing that. It actually doesn't necessarily make it more accurate, because, again, these differences across the things there, but you might get accuracy. So it's a measure of accuracy is an important challenge of when you have the multi-constellation, because the real advantage of multi-constellation is availability, that you can see more satellites. So when you're in shadowed things or availability, that's really where multi-constellation has its benefits. The other challenge is multi-frequency. Okay, when you're working at L1, L2, now maybe even L5. L5 is even farther away, so you have a much wider band receiver, and all the standard issues of a wideband receiver, flatness and frequency response, group delay, all those issues, those are big challenges to the receiver designers.
John Pottle, anything to add or go in another direction on that?
Yes, thank you. Excellent answer, John. Let me come from a different perspective to complement what you said. So in a simulator, you have to set up the scenario, we call it, the test conditions. And if you're doing a GPS test, you have to set up the GPS constellation parameters, like the almanac for the right date, for example. And then you have the propagation of the signals, which are obviously, again, simulated, but you can set up atmospheric and other effects, including blockages around the vehicle. And we use the term vehicle, by which we really mean antenna. So you've got a constellation of GPS satellites propagating signals that are simulated to a simulated antenna position, which could be in open sky or surrounded by buildings, foliage, whatever. At the most basic level, adding another constellation to a test is really not difficult from a test perspective. You simply add, if you want to do GPS and GLONASS, you would add a GLONASS constellation. The GLONASS signals would then be generated however you've set them up, either default or with other effects. And let's call it the receiver end, the ground end typically, with the antenna, would not be changed because you've just got another constellation. You'd keep the vehicle and the antenna and the environment around the vehicle exactly the same. So one answer to the question is it's actually rather straightforward to do GPS, GLONASS, or indeed other constellations testing. It's just adding another constellation or two or three or other signals to the simulation, which we simulator manufacturers aim to make straightforward. Alan, I think the audio might be breaking up, so I'll just confirm if you can hear me, and if you can, I'll just put one more comment.
All right, it seems like we've lost our audio feed once more. We are again addressing this with our webinar provider, and we hope to be back on the line in just a moment.
Well, I have to apologize again for our audio presentation. We're experiencing repeated technical difficulties along the line, but if as soon as I get word, we will resume the presentation with comments from Julian Thomas at Racelogic on multi-constellation simulation, and then we'll move to the second question, which has to do with more specialized testing conditions.
Alan, if I may, I don't know how well I'm coming through, but I could maybe address the second question. If I understand, the second question was about testing with RTK solutions, which are the differential GPS system. So the answer, can that be simulated and tested? And the answer is yes. The simulator will, what it'll do, it will simulate let me just back up. The way a RTK system works is the receiver is typically called the rover. It's the moving object, and there is a base station that is providing differential corrections to the receiver. So a simulator that's testing such a thing there will simulate both the RF of the sky and simulate what are called the RTCM messages that are the correction messages. So yes, the answer is that is quite testable in most simulators, and that would be the way to test that.
All right, thanks, John. I'm informed that we're back with a clear audio signal. I'm going to turn to Julian Thomas from Racelogic for further comments on multi-constellation simulation. Julian?
Hi, Alan. Yes, I think the other companies have covered that really quite well. The only thing I suppose I can add is that one of the challenges when running multiple constellations is particularly when a constellation isn't a full constellation. It's in its early phase of development, and in future it's going to get larger. How do you then simulate the satellites that are coming up in the future? And that is especially true for Beidou and more so for Galileo. And that is something that you need to take into consideration. We have generated artificial almanacs that contain the future satellites, which do allow you to test what will happen when there's a larger number in the sky. So that's one of the other things that does need to be taken into consideration.
Thank you, Julian. Since we have you live, Julian, would you like to address the second question, which had to do with simulating differential corrections signals?
Yeah, certainly. The way we've done this in the past, because the LabSat is a live sky recorder, is we've actually recorded the augmentation signals at the same time. This can be in the form of the SBAS signals, so that's from the satellites, from things like the EGNOS and the WAS system in the US. That's just on the satellite channel, so you get that kind of for free in the RF raw signal. But the other thing that we do is we have separate recording channels that synchronize with the raw RF data, and they synchronize serial or CAN or Ethernet or something like that. So if you do have a base station or you have some service, some N-trip service that is giving you your corrections, you can record that alongside in the same stream as the RF data and replay it. And we've found that using this method, you can simulate RTK data right down to the centimeter level and reproduce that accuracy on the bench.
Thanks, Julian. John Pottle, would you like to address corrections, differential RTK? Well, we may have lost John from Spirent as well.
Oh no, I'm back.
Okay, there we go. Go ahead, John.
Apologies. Thank you, Alan. Yes, I'll keep it brief and simple. So there are really two ways using a simulator. One is to simulate differential corrections. One is to use two real RF feeds. The other is to use one RF feed and to simulate the differential corrections. So in the case where you have two RF feeds, you set up a simulation for the base station and a simulation for the rover, and then allow the real receiver in both cases to do its stuff. In the case of the rover, to generate differential corrections and get them over to the in the case of the base station, to generate the corrections and get them over to the rover. So that's like the most sophisticated way you can do it, but you can also set up simulated differential corrections, particularly easy using an RTCM type message, as John Fischer mentioned.
All right, thank you. To our audience, we've run up the full hour, but I'm going to extend another 5 or 10 minutes to cover a third question. And then after we're all done with the webinar, again, we apologize for the technical difficulties. We're going to attempt to answer further questions by asking our presenters after the webinar to compose some written answers for a blog post, and we'll send those responses to all of you who registered for the webinar. Now for our third question, for each of you to answer, there's increasing interest. We've moved from GPS to GNSS, and there is more and more interest nowadays in a multi-input positioning, navigation, and timing solution, incorporating data from other sensors besides satellites. Can you talk a little bit about simulating the environments for a multi-PNT solution, something that might incorporate data from inertial sensors or Wi-Fi or beacons or anything else similar in your testing scenario? Let's start with John Fischer.
Okay, thank you, Alan. Yes, a lot of simulators can do that. I'll take each one of the other sensors individually. For INS, whatever the accelerometer, gyroscope signals being output, A lot of simulators, including ours, will output that data as well that would match whatever scenario you're doing. I guess I would say the one real interesting area that we're looking at is the idea that doing navigation, it's starting to be called crowdsourced navigation, in which the idea that, okay, I'm a device that's on a network. I'm a node on a network, which most things are nowadays. And so even though I don't know exactly where I am, or I want something to supplement my GNSS signal, over the network, I can talk to other nodes that may know where they are and then measure my distance to them and then imply help my solution. So that's a pretty interesting advanced area that we're starting to work in, and I'd say that all the things about network delays and measuring that and synchronizing that is an area that's being tested. And so I guess the short answer to the question is yes, all of these can be tested, and many simulators will test these composite solutions.
Okay, would you like me to have a go at that one, Alan?
Yes, go ahead and answer.
Okay, this is John. Thank you. So the question is it possible to include data from other sensors, positioning sensors, like inertial, beacons, and Wi-Fi? Well, my quick answer would be yes, of course. In a little bit more detail, it's really important to write down what the test objective is in our experience if you are looking to test these other sensors. And let me illustrate that by talking about an example with inertial sensors. So if you take a device that's got GPS and inertial, in the real world, it'll be receiving GPS signals, and the inertial sensors will be putting out data consistent with the movement of the platform, whether it's a car or an aircraft or whatever. How do you simulate that? Well, one way you can do that is to know what the output data of the inertial sensors is under different conditions and simulate those. So you don't, in that case, in the test, you don't actually stimulate the inertial sensors themselves, but you just provide the outputs of those sensors to your test systems, your sensor fusion engine. That can work, but particularly for noisy MEMS type sensors, that tends to be not a very satisfactory approach. Another approach is you can actually physically move the device in the lab consistent with the motion that you're simulating. That's a lot easier for some sensors than others. So for example, for a magnetometer or a digital compass, you can put the device on a turntable fairly readily. But for accelerometers, it's extremely difficult to simulate ongoing accelerations in a lab environment consistent with what you would get over a long journey in a real world. And just one other brief comment to think about when you're testing these different sensors is GPS and other GNSSs are broadcast systems. In a way, inertial sensor outputs are broadcast as well. There's no handshaking. When you get into Wi-Fi signals, or when you get into, for example, data that's provided over a vehicle bus, like a CAN bus, it's no good just recording the data and playing it back later. The test system or the system under test often needs to take account of the handshaking and the message protocols. So it can be done, but it's just really important to write down what you are aiming to achieve what your test objective is, and make sure that the test setup you select is appropriate for that. And we can obviously advise people on that. It's not a simple area, I would suggest. Thank you.
Thanks, John. Julian Thomas from Racelogic, would you like to address the multi-PNT question?
Yeah, certainly. Our main expertise in this area is recording the real-world signal and then playing it back on the bench. So our LabSat can record lots of other data from the vehicle at the same time, and then when it's replayed on the bench, you get all of those signals synchronized. Luckily, the other side of our business is very heavily automotive data logging based, so we have vast experience of interfacing with cars, with the CAN bus of cars, and reading out information and transmitting on the CAN bus and things like that. So that is, you get that sort of expertise free really with the LabSat. So other signals you can get on the, say, on the CAN bus of the car is the wheel speed data, because a lot of the time that's incorporated in the Kalman filter routines to vastly improve the accuracy in tunnels, for example. The other solution we offer for simulation and for the replaying of the data is we have a turntable solution which turns the navigation unit, if it's got a yaw rate sensor inside, and it can also create artificial CAN signals or pulse signals from wheel speed sensors, so you can do simulation that way as well. So yeah, that's my answer on that one.
All right, thank you, Julian. I'd like to conclude the webinar now. I apologize to our audience for the technical difficulties that we did have. What we're going to do, we're going to take all of the questions and answers that we covered in the last 15 or 20 minutes. We're going to make a written transcription of that and send it to you. So if you missed something during the audio presentation, you will get it via email within the next couple of weeks. And we will, I think I'll also look at publishing some of this material in the GNSS Design and Test newsletter that's coming up, possibly even in the magazine. If you haven't received your March issue yet, and it's just coming off the presses and getting into the mail, it does have a simulation focus, and you'll see that. A lot of information from all three companies who presented here during the webinar. I want to thank each of our speakers, John Fischer from Spectracom, John Pottle from Spirent on behalf of Spirent Federal, and Julian Thomas from Racelogic for their participation. Thanks to you, our audience, for tuning in. Join us for our next webinar. We have one coming up in, I think Bethany will give the exact date, so I won't venture out on a limb, but I believe it's March 31st. And thanks again. We'll see you next time. Bethany, over to you.
Great. Thank you, Alan. And to our audience, thank you for attending. If you have any more questions, do not hesitate to contact our speakers. I just put up their emails on the slides for you now. You can also click on their email addresses in the bios on the left-hand side of your screen. An on-demand recording of today's webinar will be emailed to you tomorrow afternoon and will be available for a full year online at gpsworld.com/webinars. And as Alan said, we will also reach out to you via email in the next couple of weeks with a transcription of the Q&A so that you can have your questions answered and have those right in your inbox. If you'd like to share this webinar with your colleagues, you can do so through any of the links on the right-hand side of your screen. You can also download today's slides by clicking on the green folder icon at the dock at the bottom of your screen. We do have two webinars coming up, as Alan mentioned. The first is Thursday, March 31st at 1 p.m. Eastern, Timing and Mission Critical Systems, and that is sponsored by Microsemi. The next is Thursday, April 14th at 1 p.m. Eastern. That is BYOD, GPS Gets Real, Lessons Learned with the New Rules of GPS Data Collection, sponsored by Terrago. You can register for either of these events or view previous ones now at gpsworld.com/webinars. Thank you again for attending today's webinar, and we look forward to seeing you at a future webinar.